sir.
Next assessment was available, isn't it? The pre-stress design is available. Not only 2 people yet. Huh?
Yeah.
22, isn't it? Yeah. Let's wait a few minutes. Let's see. I think all of you should submit the first assessment now. Yeah.
Yeah.
So if you don't submit, I think that's it. I don't think we can accept anymore. Almost 2 weeks, isn't it? Not 2 weeks, but yeah. Okay. Okay. So and the next assessment item is available. We'll talk about the assessment item at 5 o'clock today. Okay, so what do you need? What is the expectation? The assessment item is given, so I will explain what you need to do at 5 o'clock.
Tomorrow?
Today.
Today?
Tomorrow, isn't it?
Yeah,
Tomorrow 5 o'clock. So tomorrow 5 o'clock. So yeah. So last week we talked about how to find out. We work out a tutorial 1, isn't it?
No.
We discussed? No?
No. Last week we didn't have a tutorial. Last week we talked about at the transfer and at the service.
Sorry? Last week what we did?
At the transfer and at the service.
Service?
Yeah. Yeah. How to find.
Only 4 today, okay. We discussed this one, isn't it?
Yeah.
Already?
Yeah.
This one? Set B, set D, yes, isn't it?
No.
Huh?
No. Just talk about bottom 5. Bottom 5.
Bottom 5.
Yeah, bottom 5.
That one. Set B. No?
Does there be? Just talk about
No?
the first equation.
We got it?
Yeah.
Yeah, so we should be able to get the same things. I think we finished this one. I told that you can do. Okay, so anyway, we'll start from here. Okay, so the last week we stopped somewhere here. Okay, so we know how to develop the Magnum diagram. Okay, how to draw the Magnum diagram. But if you want to draw the Magnum diagram, you should know the section properties. What is section property means? You should know the cross section area of the section. It can be rectangle or I section, whatever. You should be able to find out, or you should given the cross section area, second moment of area, so that you should be able to draw the Magnum diagram. Okay, but if you are not given the section, if you don't know the cross section, okay, something like you did in the RC design, what you did, you assumed. Okay, so what you did, you assumed depth in check for deflection in RC design. Okay, so here also what we do is we will assume a section. Okay, assume a section, maybe depth of the section if it is a rectangular beam. So we will assume a section. Then if you look at the inequalities, okay, so you have 4 inequalities. You already have 4 inequalities, 2 here, 2 here. Okay, so I'm talking about so this is the original form of the inequality, and I rearrange like this. Yeah, so I'm considering this inequality. This is for the top fiber. Okay, so similarly we have another one for top fiber here under the service. Under the service stage we have another inequality for the top fiber. Yeah, so I use these two together. This is for the transfers, this is for service. Yeah, so I think I explained this one. So if you multiply this equation or this inequality, if you multiply this inequality by alpha, if you multiply this inequality by alpha, alpha times pi, alpha times pi is equal to PE. Okay, alpha times pi is equal to PE. So if you multiply this inequality by alpha, then add this one and this one together. If you add this and this one after multiplying by alpha, add this inequality with this one. So the last two terms, this and this, will disappear because this will be cancelled out by this. Okay, so you will get something like this. Similarly, you can do for the bottom fiber. For the bottom fiber, multiply this inequality by alpha, multiply these inequalities by alpha, then add this one and this. If you add this one and this one, you will get this one. So we have two conditions, ZB and ZT, one for the top fiber, other one for the bottom fiber. What is that says? The first one says ZT, this is a section modulus. Okay, so this is the section modulus for the top fiber. ZT means the section modulus for the top fiber. should be larger than this value. Okay. Similarly, the section modulus for the bottom fiber should be larger than this one. So these two values does not contain the pre-stress force or eccentricity. So in these two inequalities, or in these two conditions, you can see there's no pre-stress force or eccentricity. Okay. So this is only have some moments. The one moment is service moment, other moment is transfer state moment. Yeah. So two moments and the allowable stresses. So here you don't have anything like PI or E values. Okay, PIs or E values. So if we look at these two conditions, so we know our section modulus for top and bottom fibers should be larger than this. Okay, so what we can do is we assume a section. Okay, we assume the section, or we assume a depth. Then we check with this one. Whether our assumed section satisfy these two conditions. Okay, whether our assumed section satisfied these two conditions. Okay, so if you look at that, these two conditions satisfied by your assumed section, then your section is okay. Then you can proceed to the Magnol diagram. Okay, so this is why normally we start. So if you don't know the section, first you need to do this one. Then once you confirm, then you need to go to the Magnol diagram. Okay, so that is a normal procedure. So let's look at some rule of thumb to assume the depth. So if you have a rectangular section, this is some rule of thumb. So that means you can assume a depth of the beam something like this. Okay, so this is rule of thumb. It is not exactly correct, or sometimes it might. Okay, normally if it is around 36 marks, sometimes that rule might be in the edge, but otherwise it normally to satisfy. So let's look at this tutorial. So this is the first question. I put that the solutions as well. In the pre-stress, you don't have any fixed number, okay, fixed solution, because you have large area. Say for example, within this one you can select anything. Okay, so I can select this one, and other students may select this one or a little bit up. So you can select anything, everything gives correct answer. Okay, so the tutorial solutions, I don't give all fixed numbers, but I give how to do that one and give all brought all these inequalities. Okay, so we'll work out the tutorial 1 before we go into the other part. Okay, so this is a simply supported 9-meter long beam, and the loads are given. This is superimposed dead load, and the live load also given. Okay, live load also given. So what we need to do is, we need to find out, the question is what is the pre-stress and the eccentricity. Okay, the question is estimate the initial pre-stress force and the eccentricity at the midspan, and I ask you to use a rectangular section with 300 millimeter width. Okay, so now we need to find out the initial pre-stress force. So if we want to find out initial pre-stress force, what we need to do? We need to draw a Magnol diagram. Yeah? If we want to find out initial pre-stress force and the eccentricity, you need Magnol diagram. Okay, so if we go and draw the Magnol diagram, something like this. So to draw the Magnol diagram, what you need these inequalities. Yeah, something like this. So if you want to use this inequality, or this inequality, so this is y-axis. Yeah, E is in the x-axis. Yeah, but you need to know other values. The second moment of area, cross-section area. Yeah, second moment of area and the cross-section area, the YT, everything you should know. Yeah, so if you want to find out these values, if you want to find out cross-section area, I need to know the section details. Yeah, I need to know the section details. So what does that mean? I need the cross-section detail. That means the width and the depth of the rectangular beam. So the width is given as a 300, but depth is not given. Yeah, depth is not given. So what we can do? We can do. So we need to find out the depth of the beam first. Okay? Because we don't know the depth of the beam. If you know the depth of the beam, then only you should be able to find out the cross-section area and others. Yeah, so you don't know the depth of the beam, so you need to find out the depth of the beam first. Okay, so if you are not given the section, you should find out the section. So I will change the camera, give me a second. Okay, so the beam is 9 meter. So the cross section is a rectangular beam, it says. It's a 300 millimeter. Yeah? And the D is unknown. Okay? So we have loads. Superimpose so you are given like this. So I need to find out a suitable section. Okay. So I will assume D is equal to 400 millimeter. Okay. I don't know the depth. We will start with the smaller sections. Okay, we'll start with the smaller sections. So if we start with the smaller section, so I use DS 400. So what we need to do? So I need to derive this one, okay? ZT should be larger than MS because I already derived this one during the class last week, yeah? So because it's the same simply supported one, okay? If it is an assignment, you need to derive from first step, okay? First principle. Don't write from the lecture notes, okay? But since I already explained how to do it, I will use this one as it is. And ZB so if you look at these two, all these values are given. Yeah. So this is compression at service. So this is 20 MPa. And this one is tension at transfer, 2.5. This one is compression at transfer, 20 MPa. Tension at service, 2 MPa. Yeah, that is given in the tutorial. Yeah, so you can see the values are given here. Yeah, so these numbers. What about the alpha? Alpha also given. Here it says take the 15% as a loss. So if the loss is 15%, alpha is equal to 0.85. Yeah, 1 minus 15%. So you have all the values at the bottom. Yeah, and we need this and this. So MS, MD. Okay, so we'll find out self height first. Self height is area times concrete. Area 300 and 400. So 0.3 times 0.4. Okay. So this is 0.12. 0.12 times 24, 1288. So okay, that is a self height. Yeah. So then if you work out the MD, whereas it is a simply supported, this is a simply supported, so the maximum moment will be in the mid span. Yeah, so that is equal to WL squared by 8. W is the self height only, W is a self height, so 2.88 times 9 squared upon 8. Okay. So if you work out how much it will come. Hmm?
16. 28.
28,
29.16.
29.660.
16. 16.
16.
Yeah.
Okay. So this is kilonewton meter. Okay. So this is MD. So we know that one as well. Yeah. So now I need to find out MS. What is MS? Service moment. Yeah. So at service, MS. Moment during the service load. Yeah. At service stage, W is what is G plus long term times Q. Yeah. So because I don't know the purpose of this, so I will use 1, so G plus Q. Okay, the maximum load. So what is G? G is the total dead load. So here the self weight is 2.88 plus 5 plus 20. Q is 20. So this is 27.88 kilonewton per meter So ms is equal to WL squared by 8, but the W is equal to 27.88 times 9 squared upon 8. So 27.88 times 9 squared.
282 point 282
Point
200
200.
82. Yeah.
It's
Or
okay.
85. 285. Oh no 282.285.
Okay, I'll put 9. Okay.
Okay.
So kilonewton meter. So that is ms. So this is the moment during service. This is moment. So I need to find out what is the requirement for ZT and what is the requirement for ZP. For top fiber, ZT should be larger than ms alpha times so just look at this one. Point 0.85 times 27.88 So 282.29 minus
11.6.
no, so can you tell me this one only?
This one is 258.59.
59?
Yeah. This one is 22.13.
30?
No,
13?
131. 13.
Yeah.
13.
Okay, yeah. So, and if you get this one, this is kilonewton meter, so 10 to the power 6. So 10 to the power 6 will be there because this is kilonewton meter. Okay, all are kilonewton meter. I change it to Newton millimeter. So you will get 11 point something.
69.
One.
Oh, 69. Yeah.
6.
11.69.
Yeah.
Yeah.
10 to the power 6 millimeter cube. So my ZT should be larger than 11.69 10 to the power 6. So similarly for bottom fiber, ZB should be larger than, so if you put MS 282.29 minus this will be 258.59 bottom one 19.
Yeah, 19.
So if you solve this one, 13 point, how much?
Hold on. 61.
61.
Yeah.
So what is that says? If I assume 400 millimeter, okay, if I assume 400 millimeter depth, according to the condition we derive, the top fiber section modulus at T should be larger than 11.69 times 10 to the power 6. The bottom one should be larger than 13.61. Yeah. So this is requirement. Yeah. Let's say what is my Z is. So Z for this one, section modulus for rectangular section. ZT and ZB both are same for the rectangular section. Okay. For rectangular section, both are same. If it is different, you'll have different values. So this is B D squared upon 6. B is 300. D is equal to 400. So this is a section modulus, okay? BD squared upon 6. So Z is equal to I upon Y. I is equal to BD cube upon 12. And this is D, so this is BD squared upon 6. Okay, so this is, if you don't know how that BD squared upon 6 comes, this is the okay.
Here is 48.
Yeah, so you get 48 up.
Oh, no, the top.
I don't know, total 40,
Total.
so 48 means 8.
8.
10 to the power 6.
Yeah.
Okay. So we have 8, but we need 13 and 11. For top 11, for bottom 13, 10 to the power 6. Huh? So our rectangular section have only 8. Top and bottoms both are same. Okay. We have only 8, but we need this much and this much in top and bottom. Yeah. So our section is not satisfied. Okay. So D is equal to 400 is not suitable because it's not enough. Yeah. This value should be larger than this one and this one.
Yeah.
So now I am going to increase this one. Okay. So the question is, should I do all this calculation? Okay. So now just look at this one. I'm going to change this one to 500. Okay. Don't do that one. Just have a look. So my question is, everything will change. So should I calculate everything again? Okay. Yeah. Let's see. Okay. Let's see. So I will try for 1. This one is 0.5. Yeah.
Yeah.
So what we will get? 0.5, 0.15, 3.6. Huh?
Yeah.
So that is 3.6 and this is 3.6 here. So how much you will get? 3.6 times
36.45.
so okay 36.45.
Yeah, 45.
So that's, yeah. So here it become 3.6, nothing will change here.
No.
Yeah. So this become 28.6.
Yeah.
So this is 28.6. So how much this one?
289.58.
Okay. So here this is 289.58 and this one is 36.45. Yeah.
Yeah.
So how much we will get on the top? 200 50
258.6.
6.
Yeah.
So it doesn't change much, yeah.
Yeah.
So you can see I change the D, yeah,
Yeah.
by 100, yeah, about 25% increase.
Yeah.
Yeah, 25% increase. But if I work out, the requirement doesn't change, maybe a little bit increased. Yeah, 11.7.
11.7.
Yeah, 7. And this one also maybe 13.
Maybe it's same, just 11.69.
Yeah, so almost. Yeah, so it doesn't change much. Yeah.
Yeah.
So the requirement doesn't change. You can see the requirement doesn't change. Yeah.
Yeah.
But what will happen here? So this become 12.
Yeah, 12.5.
12.5. So you can see this increased 8 to 12 point. It's a quite large increase. Yeah.
Yeah.
But these things are not changing. Yeah. So it's little. So very small change here. So if we change the section, the requirement may not change by a significant number. Okay, so what you need can see the requirement doesn't change much. So that means you assume a section 400 and you found out the requirement, yeah? Then you increase the section, but you don't need to do all the calculation again because it won't change. Yeah? It might change a little bit, but it's not much. So it's no point of working all these values again. So rather just do this one. So now it's a 12.5. Okay? So 12.5 is larger than this, but it is smaller than this, not enough. Yeah? It's not enough yet. This is okay, this is not okay.
Yeah.
So D 500 is also not suitable. Yeah?
Yeah.
So now I am going to try D 600. So if it is D 600, how much this one? I don't need to do everything. So how much this will come? If it is 600, 18?
18.
18. So we get 18 times. So the 18 is larger than this and this. Okay? This might change a little bit, but not much. Okay? Maybe 11.72. I don't worry about 72. Okay? it's still 11 point something. This is 13.62 or 65 whatever, but still it is the 18 is large.
Yeah.
So is suitable. So you don't need to do all the calculation every time. Do it once.
Okay.
Then you, if it is not satisfied, increase to the next one. Check whether that is okay. Yeah. Then you, if not, go. So these calculations need to be done only once. Clear? You don't need to redo everything again and again, because it won't change by a significant number. It will change. Okay, I don't say it won't change. It will change, but it will change by a small number. Okay? So the moments increasing, but the difference in the moments will not change by a significant amount. So I can find out the suitable section using trial and error. Okay, we'll start with the smaller one and increase little bit little. Okay, you don't need to do all the calculation again for each and every increment. One trial is enough. Then just need to check whether it's 500 is okay, 600 is okay. If it is not 700, 800 like that, or you only need to change these values. Okay, this you don't need to worry. It may change, it will by a little bit. Okay, so now we have the section. We have the section. So if we have this section, now the question is, okay, we need to find out for the simply supported beam. I already derived but the inequalities. Okay, inequalities are already there, so you don't need to worry, because the so these inequalities are there. Okay, so this one I explained how to do this one. Yeah, this is for simply supported. Yeah, okay, so you know all the values, you know YT, I. So here the YT is this one, this is YB. So YT is 300, YB 300, I BD squared upon 12. So you should be able to calculate all the values and substitute in the equations. Okay, or in the inequalities. So you know the MD value. Yeah, you should be able to find out. For 600 you need to find out MD. For 600 you need to find out MD. Yeah, so 600 you need to find out MS. Yeah, so I already found for 500. This is 500. Yeah, so now you need to find out all these values and substitute in that inequalities. Substitute in the inequalities. Okay?
The MD and MS, the equation of MD and MS is same with performance.
This one.
Yeah, it's same.
This
with
is
this one.
MD.
Yeah.
This is MS.
Okay.
But this is, it should be for 600. Okay? So this is for 500.
Yeah.
So you need to find out for 600.
I mean, the equation is same. Yeah.
Yeah.
Okay.
Because it's a simply supported. Yeah. So you'll find out. You will find out and substitute in that inequalities. You will have 4 lines. That lines are given in the website. The model is open, isn't it? The model is on.
Development?
Can you see that previous lectures or not yet? No?
No.
Okay, I'll operate back.
Yeah, you will upload.
Yeah, sorry. This one you will get. So you should be able to see that this will be available in the Moodle. Okay. So this is the tutorial question I put it. Yep. And the solution I work out everything. Yep. And if you substitute in these 4 inequalities, you will get this, something like this. Okay, so you will get these 4 inequalities. You will get these 4 inequalities. So if you have these 4 inequalities, you should be able to draw the lines. Yeah. Yes. The first one, second, third, fourth, and draw them, and you will get the Maxwell diagram. Okay, you will draw the Maxwell diagram and get the P and E value. As I told, there are lots of different values are possible. Okay, so I leave that one. So you will draw something like this. So you will draw E versus 1 upon Pi. Okay. So the first line, if you draw them, it will go like that. It is the first one. So it is above the line. Second one will be
This way. Okay.
yeah, so the slope is smaller. Okay, so that is second one. Third one will be like that, and the fourth one is this is fourth one, that is the third one. Okay, so it will tell that this side, this will tell below the line. So you have this feasible area, something like that. Okay, draw that one in an Excel or graph sheet. Okay, so then you should be able to select value. So the E maximum, in your case, it can't go more than 300, isn't it? Maybe if you have some cover, so let's say you have about 40 mil or something, yeah. So it can't go more than 260. Yep, isn't it? Because maximum is 300, but if you need some cover, so it can't go more than 260. So maximum E is 260. Yeah. So anything this side, so normally we will go somewhere there. Okay. So 2:1. 2:1. So this one will give you yeah. So this is your E, this is your 1/pi and E. If you know the 1/pi and E, you should be able to find out. You should be able to find out pi. Okay. So I will put this. This is already there, so I just need to open the time. So when you have that one, you should be able to access this tutorial. Is it clear? Any questions? All good? Okay. So if you have, so this is what we worked out. So we know how to find out a suitable section, how to find out the PI and E values. Okay. So remember, for your assignment, I'm not sure how many of you look at, you need to use the standard I sections. I'll talk about this one tomorrow, but you might need to use I section. Okay, so in this case, they gave what is ZT and ZB. You don't need to calculate; they are given. Cross section area is given. Okay, so if you look at that the question, you have this section details. Okay. In the assignment, how many of you look at the assignment? Have you looked at that one?
Yeah.
So you have the so you will get something like this. Wait. Stop So this is the I sections. These are the standard I section we normally use in the bridges. Okay, so these are the standard I section. There are type 1, 2, 3, 4. These are the standard I sections we normally use in the bridge construction. So you should be able to get this one from AS 5100. So you should be able to get this one from the AS 5100 part 5. Okay, so these are the standard sections. So here they gave the set T and set B. The first one is a set T, they call as a set superstructure. Super means top and the other one is sub, means bottom. Okay, the first one is the top one and second one is the bottom one. Okay, this is set T, this is set T, and this is set B.
Set T, set B.
Yeah, so this one is set T, and this is set B. Okay, and this is YB. This is I. This is A. Okay. So if you are not sure what is the notation means, okay. So the set T, set B, everything is given. Set B is given. So you should be able to find out set T, isn't it? The total is 750. Yeah. Say for example, here's total is 750. YB is 337. Yeah. So you should be able to find out what is the rest. Yeah. 413. Yeah. YT is 413. Yeah. YT here, the first one, because 750 is the total depth. You can see the total depth is 750.
Yeah.
So bottom is 337 YB. So the rest
Half of
413. If you add YB and YT, you will get 750, isn't it? Okay. If it is a rectangle, only half. This is not rectangle. Okay. YB is given.
Yeah.
And the total depth is given.
Yeah.
So you can find out what is YT, isn't it?
Yeah.
So it's addition should be 750.
Yes.
So you should be able to work out. First you need to look at the section and see whether it's suitable or not. Okay, even in this question, if you want to use I section, you should be able to work out. Okay. So normally in the bridges we use I section, not the rectangular section. Okay, because I sections are more economical in terms of self-weight and others. Okay, so that's about the section selection of the section. Okay, selection of the section, and how to find out the pre-stress force. Yeah? Any questions? So this is called initial pre-stress design. Initial pre-stress design. So in this one, we know how to select a suitable section and how to find out initial pre-stress force and how to find out initial eccentricity. Yeah? So not initial, what is the eccentricity? Shall we move on? Yeah.
Second question about the initial pre-stress force and
Yeah, initial pre-stress. That's what.
Yeah.
In the here.
oh.
This is the initial pre-stress force. This is the eccentricity. Yeah. So if you draw the Macron diagram, you will get it. Yeah.
Yeah.
So it can be many points that you can select. Another student can select here, here. Yeah. So there is multiple correct numbers. Okay. Okay. Any questions? If not, let's move on. So the next one, okay, now we have the section. We also found how much force we need to apply. Yeah. So the next question is the tenets. Because we apply the pre-stress force using tenets. Yeah. So the steel tenets. Yeah. So we apply the pre-stress force using steel tenets. So in this one, in this section, we'll talk about tenon properties and how to select the tenets and how to put them and some end anchorage system. Okay. So let's look at those things. So before we go into that one, and again I just want to make sure you understand the terminology. We had three terms. One is wire, the second one is strands, third one is tendon. So this one is a strand. Okay. So if you look at this one, okay, if you look at this one, oh, sorry. So if you look at this one, you can see there are 7 wires. Yeah, 7 wires. They are twisted. Yeah, you can see the twisting, the 7 wires. So we have 7 wires. And made of one strand. So this is called strand. So if you look at this one, so this is called one tenon. Okay? Tenon. T-E-N-T-O-N. Tenon. Okay? Tenon. So this one have multiple strands. Okay? You can see there are multiple strands. This is one strand, this is a strand here. it is here. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 or 12 or 13, something like that. Yeah. So this all together we call as a tenon. So you can see that all these strands goes through a small duct. Yeah, it will go as a single unit. Yeah. So here at the end it looks like this, but within the beam it will go like a single unit. So this is called tenon. So the tenon properties are given in clause 3.3. Okay, clause 3.3 gives the tenon properties. That is the same section. Okay, in the section 3 you have the properties of concrete as well, but that is in 3.1, here 3.3. Okay, 3.2 is for the reinforced concrete, reinforced steel. So this is tenons. So the wires, normally we use 7 millimeter or 5 millimeter wires. Okay, 7 or 5 millimeter wires. Then couple of wires will make a strands. Yeah, couple of wires will make a strand. In Australia, the 7 wire strand is more commonly used. 7 wires. Yeah, the one I saw that one, the photo. But the strands can change the diameter because it's depend on how many wires you have. Yeah.
Yes. So
you put the number of wires and twist it and make a strand. Yeah? And then the pre-stressing bars normally we use if you have straight tenons. That is separate. Okay. So the wires, couple of wires will make strands, couple of strands will make tenon. Yeah? And the properties are given, and you can see this is the normal reinforced concrete one, and this is the pre-stressed one. Pre-stressed one is much larger. Yeah? Yeah. And you can see the cracking will occur at higher load because of the initial pre-stress. You know, due to initial pre-stress, the curvature will be in the opposite direction. Yeah. So the cracking will occur at a large load, much larger load. So that means cracking load or cracking moment is much higher. So how to find out the tenons? So the arrangements, if you have, say in this one, 6, in this one 6 tenons. Yeah, 6 tenons. Each tenons may have couple of strands, and each strands may have a couple of wires. Yeah. So now today we are going to look at how to find out the number of tenons and how to arrange them. Yeah, we need to arrange them in the cross section. Okay, so first we need to find out how many tenons we need, then we can decide how to arrange them. Yeah? Yeah. So let's look at so we have a beam I use to explain something like this. Yeah, simply supported. At this location I know Pi and eccentricity. Yeah, this is the critical section. This is the critical section, maximum moment. Yeah, at this location I found the Pi and eccentricity using Magnol diagram. Yeah. So if you find that one, now the question is how many wires we need. Okay, just to explain, don't worry about it. To explain, I use a value here, 5000 kilonewton, let's say. Okay, just to explain, I use 5000. So I need to apply 5000 kilonewton load. I need to apply 5000 kilonewton load, yeah, at the mid span here. Yeah, but the steel, I can't apply anything here because the steel will come from the end. Okay, I don't know how that will come, but let's say you put the wires something like this. Yeah, the shape I don't know at the moment. Yeah, so the steel wire, you put the pipe and put the steel wire and fixed one end. Yeah, and pull that one, isn't it? Yeah, isn't it? That is how we do the post tension. Yeah, if it is a pre-stress, pre-tensioning, we just stretch the steel first and put the concrete. Yeah, should be okay. But in that case, from here to there, same pre-stress. If it is a pre-tension, it will be same load from here to there. Yeah, but when you work out for the post tension case, you will put a duct. Yeah, you will put a duct, isn't it, like a pipe, and put the steel through that. So when you have a pipe and you insert the steel through that, and when you pull that one, what will happen? There will be some friction. Yeah, there will be some friction loss. Yeah, friction. Yeah, so when you have a pipe and you insert the steel and you apply the force there, what will happen? The steel wire and the duct might touch each other. Yeah, when you have two objects touch each other and try to move, relate to the other one, there will be a friction loss. Yeah, understand? There will be some friction loss. So if you have a friction loss, so if you apply something here, that will reduce over the length because there will be a friction loss. Yeah, there will be a friction loss. So if the friction loss is, let's say this is about 5%. Yeah, if you have 5% loss from here to there, and you need to have 5000 here, so how much you need to apply? More than 5000. Yeah.
Yeah.
So how much I'll apply this one Pj. So Pj is equal to 5000 divided by, if the loss is 5%, 1 minus 5%. So 5000 divided by 0.95. Yeah. So if you apply 200.
Yeah, 63.
63.
Yeah, 63.
So you need to apply this much of load here, then 5% loss you will get 5000 the mid span. Okay, so I need to apply 5263. How that comes? That is Pi, so Pj Pi divided by 1 minus
Loss.
friction loss. Yeah, friction loss. Pi 1 minus friction loss. Okay, I need to find out Pj. So in the standard AS3600, if you go to the AS3600, there is a formula for friction loss. Okay, there is a equation for the friction loss. We will talk about that one in week 10 or 11. We might talk that one next week. Okay, so the friction loss, then equation. So you should be able to find out how much force you need to apply at the one end. Is that okay? Any questions? Okay, now I need to apply this much of force. Let's say 5263 kilonewton. Okay, so how many wires I need? How many wires I need? So if you want to find out number of wires, if you need the number of wires, give me a second. There is a standard AS3600. So if you go to the AS3600, (3.3) properties of tenants here. They gave the properties of tenants. Okay, so we are using 7 wire strands. This one, yeah, 7 wire strands. So if you have this one, and normally we use 12.7 millimeter diameter. This is the standard strand. Yeah. Other one is as 15.2. These are the two normally used in presters. Okay. So this is 12.7 millimeter wire. That gives a breaking load of 184 kilonewton. Okay. So what does that mean? At 184 kilonewton, it will break. Okay, fail. So if you want to apply 5263, yeah, you may need lots of strands, isn't it? Each one can go up to 184. Yeah. But another important things here, the strands properties. The stress strain relationship of the strand, if you apply, it will go like this. So this is the breaking load. Breaking point. Okay, so this is the breaking point. What is the yielding point? if you have something like that, we don't have any yielding point. What we do is we will use 1% proof stress. Okay, this is a strain, so 0.001, that means 1%. 1%. So here you have a slope, and we draw a parallel line to that initial slope. So this is called proof stress. So this value is called 0.1% proof stress. Okay, 0.1% of proof stress. Is it clear? So it is 0.1% of the proof stress. So this is also called FPY, yield stress. Kind of, not exactly yielding stress, but this is the equivalent of the yield stress in this material. Okay, if your material don't have a clear yielding point, we should use the proof stress as a yielding point. Okay, so this is the breaking point, this is the yielding point. Okay, yeah, in the standard they gave the breaking point, so kilonewton. Yeah, and they also give the proof stress detail here. So for the strands they say 0.82 of the breaking load. Okay, this is the PB is the breaking, P is the pre-stress, B is the breaking stress. So yield stress PY is a yielding stress. The yield stress PY, P is the pre-stress, Y is the yielding. Okay, so the yielding strength is given by 82% of the breaking stress. Okay, so that means if the breaking load is 184, yeah, your yield load will be 82% of this one. Okay, so So 184 times 0.82. So how much you will get? Can you tell me?
150.9.
So this is your yielding load. Okay. So each strand can go up to 184, but the yielding point is 150.9. Yeah, 150.9. So when you stretch the steel, you are stretching the steel. Yeah. So you want to go up to here or somewhere here. Normally we don't want to go more than that. Okay. This is a yielding point. After that, quite danger, it will fail. Yeah. So we don't want to go near to this. So we want to limit our pre-stress somewhere here. Okay. So we want to limit our pre-stress somewhere here. So what is the load I can apply? 150.9. Yeah. I don't want to apply anything more than that one. So the number of strands Pj yeah times area, yeah, the load. So in this case, what is a Pj? 5263. The load is 150.9. So you should be able to find out how many strands you need. Each strand you can apply this much. Yeah. Yeah, because of the stress I put area. Okay. So the load, this is load, applied load divided by yielding load. Applied load divided by yielding load. You may get how many?
34.9.
So I will use 35 or 36. Yeah. So I will use, better to use 36. So 36 strands you need. 36 strands you need. So each tendons may have 6 or 7 or 12 strands. Yeah. We look at that one last and
36.
yeah. So we look at this one. Each strands may have 6 or 7 or 8. There are different numbers. So at let's say 12 strands. So you need 36 strands total. Each one will have 12. So we need 3 of them. Yeah. We need 3 of them. So this is how we calculate. This is how we calculate the number of tenants. Okay. So to apply okay. Clear? So now the question is how to arrange them. Yeah. So we have the this is 300. Yeah. So for example, just say 600. So we need 3 tenants. Yeah. So each tenants will have 12 strands. Yeah. Something like that. Yeah. So I need to arrange them here. So how to arrange? So I found the eccentricity. Yeah, I found the eccentricity somewhere here. Yeah. So I need to put, technically I need to apply this one, all these ones here. Yeah. But can I apply all 3 in one line? Is it possible? Maybe, but not sure. It's depend on the diameter, yeah, and the width, yeah. So you normally you can't put it because it's 100. Then you need the cover as well. So it is difficult to put all 3 in one line. So what I can do? So it is not possible. So I can put them something like this. Yeah. If I can put 2 in a line, or if you can't, I need to put like this. Yeah. This one or this one. So how to decide, or how to, okay, let's say it is possible. So in the rectangular section, the E value is here, the resultant should be there. Okay, so total P you will apply by P by 3, P by 3, P by 3, isn't it? Total force, you use the 3, so you divide this one into 3, apply for each one, so total will be there. So if you want to apply all equal, if you apply 3, the resultant will be somewhere here. Yeah. The resultant will be there. So the resultant should be there. So you need to arrange them so if you arrange like this only, the resultant will be there. Okay. So you need to adjust this one so that the resultant comes to the E. This is you already calculated from the Magnell diagram. Okay. From the Magnell diagram you know the eccentricity. So now you need to put that tenants so that the resultant comes here. If it is a rectangle, this is 2:1, yeah? 2:1. So if it is a rectangle, it's a 2:1. Yeah? So you may need to provide the tenants even below the E eccentricity. Okay? And if you have something like this, E is here. Yeah. So you need to provide something like that so that middle. Yeah. So the resultant will be in the middle. Okay. this is how we arrange the tenants. So when you arrange the tenant, the resultant should be match the eccentricity. Okay. So now what we learn how to find out the number of tenants, how to select the number of tenants, and how to arrange them. Okay. So here what we learned here, when you arrange in one row, it's easier, but it is not possible always to have all in one line. Yeah. So when you arrange in different ways, the resultant should be comes to the eccentric point. Okay, eccentric point. So in that case, you may need to provide the tenants even below the eccentricity, even below the eccentricity. Yeah. So still you need to provide the cover. Still you should have the cover.
Yeah.
You need to. So you can't go to the maximum E when you're selecting the E value. So you can't go close to that one because you need to have some tolerance here. Yeah. If you select somewhere here, what will happen? You can't bring it down. Yeah. This is the maximum. If you select the E somewhere here, okay, if you select the E somewhere here, the problem is, if you, let's say you select the E, maximum E, okay, if you select the maximum E, what's the problem? You cannot put any tenants below that. Yeah. If you select the E here, you cannot put any tenants below, so these cases are not possible. Yeah. These cases are not possible. Is it clear? Yeah. So this is how we normally arrange the tenants. And tomorrow we will talk more about the tenant profile, how this tenant profile will go. So far everything is at the mid span. Okay? We'll talk about the tenant profile, and then we will work out second tutorial tomorrow. Okay? So the next week we will talk about ultimate moment and shear and losses. So that's basically enough for your assignment. And week 11 we will have some advanced topic as we discussed, and week 12 will be revision. Okay? Any questions?
So we are unable to see the pre-stress design in Moodle.
Sorry?
We are unable to see the pre-stress design.
Yeah.
in
So
Moodle.
it will be available. Sorry, I forgot to open that one. So it will be available after the class. After the class means after 7:30. I have another class, so after 7:30. Okay. Sorry for that. I forgot to open that one. Okay. The assignments are, you can see the assignment, isn't it? Are you able to see the assignment?
Yes, sir. Yeah.
Yeah. So only the PowerPoints are not there, so I will put that one. So you should be able to see after that one. Okay.
Okay. Thank you.
Anything else? Any other question?
No, sir.
Okay, so in that case we will close today and see you next, tomorrow. So I thought today is Tuesday. I don't know. So